Okay, good afternoon. So let us finish the exercise we started last time, yesterday, which is the van der Waals attraction. Okay, so attraction of two far away hydrogen atoms. So let me remind you, I have one atom here, one atom at a certain distance r. This is the Hamiltonian 1 of atom 1. This is the Hamiltonian of atom 2. I do not rewrite it, the usual hydrogen atom. And then we discovered that must be, so this is H. There must be interaction in the form of Coulomb terms. We treated this interaction, and we discovered that for very large R, you can essentially approximate everything with the following expression. E square over R cube x1 times x2 plus y1, y2 minus twice z1, z2, where I take axis z to be here in the direction of the two atoms, okay? Z, x, and y are like that. And by the way, I also, if you remember, I defined each, for instance, x1 is the x-coordinate of atom 1, which is defined with respect to the center of the atom. And similarly, x2 is the x-coordinate of atom 2, R2, okay, which is defined with respect to the center of atom 2, okay? So these are small quantities of the order of the Bohr radius. Okay, so if you remember, this is the dipole-dipole interaction that you expect for the two neutral atoms, okay? Now, this will be our unperturbed Hamiltonian, and this will be our perturbation, okay, in setting up our formula. So to the unperturbed level, for instance, the ground state, the E, how should I call it? E 0, the unperturbed thing, is just twice the energy of the hydrogen atom level number 1, okay? Remember, the 1, 0, 0 state, okay? So the minus 2 Rydberg, okay? So this is the 1s state. This is the unperturbed energy of this object. So for very, very large R, you expect to tend to this value. Now we want to calculate, for instance, the correction to this energy due to this term, okay? And we will show that this correction, so if this is the minus 2 Rydberg, which you attain for very large energy, the correction is negative, and it goes like 1 over r to the 6, okay? We'll try to estimate this constant. Not, in fact, a detailed calculation, because a full second-order calculation would be very tricky for this quantity, but the order of magnitude we will get, okay? How to do this calculation? Well, first of all, this is the first instance where we have a system with more than one electron, okay? So we have to start generalizing a little bit our machinery. We will do it in a systematic way towards the end, when we'll talk about many identical particles, fermions, bosons, things like this. For the time being, let me just give you kind of recipe. So the problem is the following. I have two Hilbert spaces. Let me erase this, okay? You know this. You have two Hilbert spaces. The Hilbert space of the particle 1, I will indicate as H1, not to be confused with the Hamiltonian, is the Hilbert space here, okay? Including the orbital and the spin degrees of freedom. And the Hilbert space of atom 2, okay? So this first electron lives in this Hilbert space. The second electron lives in that Hilbert space. You might wonder, what is the Hilbert space of the whole system, okay? The answer is the product. If you remember, we already used this construction in describing this, for instance, as H1 orbit times H1 spin, okay? And similarly, we can do for H2. Now we use one level more, and we say that when we have two independent systems like this and that, we have the product Hilbert space. Now, the systems do not necessarily have to be, by the way, independent. In fact, they are not independent. So the states belonging to this thing will be then mixed and summed together. So, but this is still the correct Hilbert space where to pose the problem, with some specification, okay? When I have two identical particles, like, for instance, the two electrons in this case, physics dictates some symmetry requirements for the wave function, which we will discuss in the late part of the course. And the symmetry requirement is that if you interchange the two electrons really have no tag on them. It's not electron number 1, okay, with the 1 depicted in red on the electron and the 2 also, okay? They have no name, and therefore they are very indistinguishable in some sense. And the physical requirement is that the wave function changes sign if you just interchange the two. They are fermions, okay? We will learn this a little bit more later on, so don't wonder now why a change of sign. There are particles for which there is no change of sign, okay? The wave function is symmetric, so +1 if you interchange. Okay, so this is, so if I ask you, for instance, forget about this term, okay? The ground state of this object, what would it be? We know the energy. The energy we said must be just twice the energy of each one of this. But what is the wave function? Well, the wave function, you might say, okay, it's the 1, 0, 0 element for the electron 1, okay? What spin? You decide. For instance, up, okay, let's say it's +1/2. The spin of the first electron is up. Now, the second electron, you put it just close by. So here, second electron, you put it also in the lowest state, 1, 0, 0. All right, second electron. What spin? Well, here there's some different possibilities. For instance, one would we say, okay, let's put it up as well. Okay. Now there is a problem. If I do that, clearly when I exchange particle 1 and particle 2, the state is exactly identical. Okay? No minus sign. And that's forbidden. Okay? So the state I just wrote, it's not possible. It's physically, you should cancel it. So not every element of the product state is actually physically meaningful. Some are not, like this. Only the ones that respect the antisymmetry, or if you want the Pauli principle, are allowed as possible candidate. So for instance, one possible object that is perfectly legitimate is the following. Rather than taking both spin up, you take the first spin up and the second, for instance, down, or the first, you take it down, and the second, you take it up, okay? And then you take 1 over square root of 2 in front, okay? So the orbits are just the same, the product of the two, okay? So if I have to write the wave function of this object here is simply the product of the wave function 1, 0, 0 for the electron 1 times the wave function 1, 0, 0 for the electron 2. But the spin, you see, is not a product. It's a sum of product. We have seen already this when we studied spin-orbit coupling, okay? Sometimes you have to work with sum of products, with states that are no longer simple products. They are called entangled, okay? This is a very important state. It's called the singlet state. In other words, the spin of the two objects is not, say, up and down, but is a combination of up, down, and down, up, okay? So if you ask, what is the spin of the first state? The answer is, it could be up or down, half and half, if you measure, okay? Notice this minus sign. Why there is a minus sign? In principle, there is also another state that has a plus sign. It's a legitimate spin state, but the plus sign for the spin state is not good for this orbital wave function, because this is symmetric under exchange of 1 and 2, and therefore this part of the state must be antisymmetric in order to be fully antisymmetric, okay? You want the full state to be changing sign if you interchange 1 and 2. This doesn't change sign, therefore this has to change sign, okay? And the singlet state changes sign, yes? Yes. You can have triplet states. The plus ones are called triplets, okay? We'll do it later on when we will do many particles. You take 2 spin 1/2 and construct triplet and singlet state. It's an identical procedure to the addition of angular momenta we did for spin-orbit coupling, okay? It's simply addition of 2 spins, okay? From 2 spin 1/2, we get spin 1 and spin 0. And you can do the same thing, exactly identical. So that thing is possible if this object here becomes antisymmetric, okay? So you can take 2 different orbitals, antisymmetrize them with a minus sign here, and therefore the symmetric part, spin part, is a possible object, okay? But in general, it's more complicated. I mean, life is more complicated when you have more than one particle and spin, because you have to take care of this requirement of antisymmetry. This is the reason why people invented second quantization, okay? Because doing this in the way I have written, okay, it's, you see, quite laborious. You have to say, but here I have to have a plus, then therefore I have to have a minus there. It's a complicated thing, and if you have 3 particles, 4 particles, it becomes a mess. You realize you have every single pair can be exchanged, but you have to have a minus sign. For 2 is a manageable thing, but if you start having more than 2 identical particles, the requirement imposes every single exchange to change a sign of the thing. It becomes a very, very tricky business, okay? With second quantization, everything simplifies a lot, but this later on, okay? Now, let me just finalize this discussion. So this is a legitimate state, okay? Singlet for the spin, so the 2 spins are up, down, minus, down, up, okay? Times an orbit which is perfectly symmetric for the ground state, obviously. But what about other excited states, okay? Well, in principle, you can form many states if the orbits are different. The orbitals are different. For instance, the spin might be plus, the spin might be even parallel, okay, both up or both down, okay? So you can form many states. Nevertheless, the problem we are confronting with, you see, it's a purely orbital object. The spin is not involved at all, okay? So whatever spin state you have here in this part, remember, we'll try to calculate, for instance, to second order, E2 of the ground state will be minus the sum over all states M different from the ground state of some matrix element. Let me just denote it as, so ground state M modulo square times E0 M minus E0, 0. This is what we'll try to calculate. Each of those single things is a 2-electron state, not a single electron state, okay? So you will realize that the spin appearing here and the spin appearing there, okay, just have to match together, okay? So for instance, the ground state is a singlet, and all those states appearing there have to be singlets. Otherwise, they would not, I mean, the overlap would be 0, okay? So in some sense, all the states that I will be constructing are something times a singlet, okay? So the singlet is already antisymmetric, and therefore the something here must be symmetric. So if I have 2 identical particles, automatically symmetric. If I have 2 different particles, I have to sum with the square root of 2 and invert the thing. So for instance, if I have a level 1s and a level 2s, just to tell you something, then I would have psi 2, 0, 0, R1, psi 1, 0, 0, R2, okay, plus psi 1, 0, 0, R1, psi 2, 0, 0, R2, 1 over root 2. You see, this is perfectly symmetric now, although the 2 orbitals are different. Well, this can be done, can be taken care of, but there is really no big subtleties connected to symmetries and anti-symmetry here. So for the purpose of this calculation, you can essentially forget about this issue about spin, anti-symmetry, and everything else, and assume that they essentially have, for instance, these 2 electrons there. So forget about really this complication, okay? And think of the 2 particles as being distinguishable, kind of, okay? So no subtleties of symmetrization and things are important in this particular problem, okay? They're important in general, but not here, okay? So I would close this parenthesis, this anticipation of many particle system, with some caveats, but in general, in this case, you need not to worry, okay? But still, I have to keep matrix element with many excited states. So how do you form excited states? Okay, I have here my atom 1, and here my atom 2, okay? So the ground state is I put an electron in the 1s here and there, okay? So for instance, up, down, minus, down, up, okay? Good, so this is the 1s. Then I have the 2s that is here somewhere, and the 2p. And I have here similarly the 2s and the 2p, okay? So for instance, I can put excited states. I can put the first electron there and the second there. Or vice versa, the first there and the second there. Or both there. Or 3s, 3p, 3d, okay? Clear? So you have many choices. You can put every single electron in one of the excited states here, and the other electron also in one of the excited states. Each will have a certain energy, okay? So if I put an electron, for instance, here, and the other electron there, or there, the energy will be E. If this, I call it E1, This I call it E2. This I call it E3. Remember, En is just equal to minus the Rydberg divided by n squared. Okay? So the energy of this configuration there would be E2 plus E3. They're negative, obviously, but okay, because of this. The energy of this and that would be twice E3, and so forth. Okay? And this should be put in the energy denominators there. And the wave functions that I select are used in calculating the matrix element. Okay? And I should sum over all possible states of this type. Okay? The possible M that you can form are putting one electron in any state for electron 1 and for electron 2. All right? So an infinite sum. So you immediately wonder which terms in the sum are different from 0. Well, one can prove the following thing. First of all, remember, these objects are products, products wave function, okay? The operator also is made of products. You see, x1, x2, or y1, y2, or z1, z2, okay? So what does it mean to calculate that matrix element? Let's make an example, okay? Suppose that I want to calculate V. The ground state is 1s and 1s, okay, for both electrons. And the, for instance, the excited state is some n prime, L prime, M prime for electron 1, and n prime or n second, well, let me call it just N1, L1, M1, and 2, L2, M2. Okay? I just give you the number, okay, for the level. All right? Good. So I should calculate this thing. What does it mean, really? This is a double integral, first of all, because you have to integrate on electron 1 and electron 2. Okay? On the right, I have what? I have a product wave function, which is the psi 1, 0, 0, R1 times the psi 1, 0, 0, R2. Okay? In the middle, I have this beast here. Okay? So for instance, let's consider one element, the Z1, Z2. So in the middle, I have an element like Z1, Z2. Okay? And on the left here, I have another product, two wave functions, one for R1 and another for R2. Okay? R1 is, for instance, in element N1, L1, M1, and R2 is in L2, L2, M2. Okay? So this is in principle the matrix element. Not a single integral, but a double integral. However, you see it's very factorized. Okay? So for instance, electron 1 cares about this Z1 and the other state on the right. And electron 2 cares only of this Z2 and the state on the right. Okay? So in some sense, this is nothing but a product of two single electron integrals. One is N1, L1, M1 times Z1 times 1, 0, 0, and another, which is N2, L2, M2 times Z2 times 1, 0, 0. Okay? Is it clear? So the first thing that you notice that due to the factorization of the states and the factorization of the object there, the matrix elements are really factor of simpler integrals. All right? So you have to only consider which objects do really appear there. So for instance, question, every n1, L1, M1 will have a matrix element like that or not? That is a typical thing of selection rules. Maybe with a selection rule I can tell in advance, without calculating this thing, to discover that, for instance, it's 0, that the thing is 0. Well, there is an obvious selection rule. Z is odd. The ground state is L equals 0, is even. Okay? So if this is even, an even function, like, for instance, L1 could be, again, 0, 2, 4, any even spherical harmonics is an even function, then this should be 0. Okay? So you immediately show that half of the things you don't care. Okay? All the states like the D states, okay, the S states, no contribution. All right? Still, there are the P states, the F, and so on. And there comes a second selection rule. This time is due to angular momentum. The selection rule, I will just tell you and show it to you, but I'm not going to prove it to you in general, because it would require a little bit of complicated concepts of angular momentum, like Wigner-Eckert theorem and things like this. Okay? So I will not enter into this discussion, which is one of the standard topics in more advanced angular momentum treatments. Okay? I will not do that. But what I suggest you is the following. First of all, 1, 0, 0 is a spherically symmetric S wave. Okay? Z is what? Z1 is really R1 times the cosine of theta 1. Okay? So what you realize that what I have there is a certain radial function, the 1s radial function, times the 0, 0 spherical harmonics. Let me omit the index 1, okay? It's electron number 1. Okay, times what? Times the n1 L1 spherical radial function times the L1 M1 spherical harmonics, and all this should be integrated in dr1 times r1 square, and integrated also in d theta sine theta and in d phi. Okay, from 0 to 2 pi and from 0 to pi. Is this clear to everybody, what I wrote? Okay? I took this integral and I wrote it explicitly for you. There. Integral, the radial function, well, these are real, but okay, times the z1, which is r1 times the cosine. So you see, this thing with this and with that, they really take care of the radial part. Okay? Some integral, we don't care. But let us look at the angular part. Okay? The angular part is, well, really this is a constant, 1 over root of 4 pi. Okay? So the angular part is a cosine theta with the spherical harmonics L1, M1. Okay? But you remember that cosine theta indeed is a spherical harmonics itself. Which one is it? Apart from a factor. Huh? The 1, 0. Okay? So apart from a factor, which I don't care, is the 1, 0 function. Okay? So apart from a factor, so there is a radial integral. Okay? There is some factors. 1 over 4 pi and other factors, square root of something for this to become that. Then you have this integral of, well, let me write it with more space. Integral in d theta sine theta, integral in d phi of y star L1 M1 theta phi y1, 0, theta and phi. So now the question, which L1 will contribute to this integral? Only one, okay? So not all the odd ones. Here, in principle, I would say, okay, maybe 1, 3, 5, all contribute. Now I discover a further selection rule. Only one can contribute. One, I mean the p states, okay? So starting from the S state, the operator Z1 can only couple me to p states, okay? That's quite important. For instance, if I have a momentum operator, okay, and I have some S state here, question, which other states can have a matrix element that is different from 0? The answer is exactly identical. P states should go here, because this is L equals 0. This is a vector, okay? A vector operator is like having an L equal 1. So L equals 0 plus L equal 1, or times L equal 1, really produces for me an L equal 1 here, okay? So this is, well, a kind of hand-waving derivation of a result that is due to Wigner and Eckert that tells that essentially the structure of matrix element like this is all dictated by what kind of operators you have there. If it is a scalar, if it is a vector, if it is a tensor of rank 2, okay, then maybe it has angular momentum L equal 2, and so on and so forth, okay? So you can classify operators as well as states in terms of how they behave under angular momentum, okay? Now, this is not something we'll do, but be aware of the fact that an operator like X, okay, or Y or Z, so the operator R or the operator P, both are vector operators and they behave as L equal 1. And so when they act on a certain state, they can change the angular momentum essentially by plus or minus 1. Okay? In this case, from L equals 0, you can just go to 1. Okay? But if you start from L equal 3, for instance, apply a vector operator, you can go to 4, 3, and 2 in principle by composition of angular momentum. This is, again, not something that you should supposed to know, but at least have a vague acquaintance to this fact. Okay, in this case, we just derived because it was simple. This is just 0, 0 is a constant, so we know that these two states are orthogonal, okay? You realize that if I have a third spherical harmonics and not just a constant, then the result is less trivial, but it's still true, okay? So the product of three spherical harmonics has some rules on what are the indices that make the integral different from 0, okay? These are called angular momentum selection rules. They're useful in atomic calculations, for instance, because you never start calculating a matrix element when you see that the angular momenta of the two states that you are considering differs by more than what the operators allows you to do. Okay, so to conclude, of all these intermediate states that you want to keep in the sum, the ones, okay, which are important are only those for which L1 and L2 are just 1, okay? All right? You might say, okay, you derive this for Z1. What about X? Well, for X it would be identical, except that when I have here X, then I write as Y1, 1, and Y1, 1 minus 1, okay? So instead of 1, 0, I have a combination of two of the other ones, but obviously still L should be 1, okay? So in all cases, the intermediate L that I should think of summing is 1. Still, it's a very complicated sum. You realize that I have to sum, for instance, for this, the P states here, and for instance, a P states there, or a P states here, and an F state here, F here and P there, and so on and so forth, okay? So all kind of higher, sorry, the F is L equal 3. I'm sorry. What I mean is that there are P states in this level, in level 2, in level 3, in level 4, and so on. Okay? So I take it back. P states only, but in every possible level there are P states. Okay? So still an infinite sum. And this would make the calculation cumbersome, because you have to calculate a certain number, infinite, of radial integrals, for instance. But they are known, they are tabulated, everything can be done, but it's painful. Now, shortcut. Rather than calculating an exact sum here, which after all is an approximation to our thing, is a second order approximation. So it's not the exact result. So there's no real urge of calculating exactly something that is already approximate. Let's approximate even more. So what do? Well, we realize the following, that these numbers here, these are the energies of the intermediate states compared to the energy of the ground state, so where the electrons stay here and there. We said the energy of the intermediate states are just given by this formula. So you see they are much smaller. For n equal 1, they would be just the ground state. But for n equal 2, it's 1/4 as smaller. N equal 3, even more. Okay? So all these numbers are much smaller than this. And therefore, I propose the following crude thing. Forget about this. These are smaller. Okay? So let's throw them away. All right? Good. Now, you might say, well, but then what? Can I still do the sum? It's still an infinite sum. I just brutally truncated the sum of the things, but still an infinite sum. Yes, now I can do it. Look at the trick. The sum that I have there, E0. Oh, by the way, I skipped one step, which I discussed yesterday. I immediately concentrate on the second order correction. Obviously, I should have discussed with you that the first order correction, okay, which is essentially, I write first the first order correction, is calculating the perturbation V between 1, 0, 0, 1, 0, 0, diagonal. Okay? In other words, the state to the right and to the left of each single electron are the same, the ground state. Then by parity, each single matrix element here is just 0. Okay? So forget about that. All right? So this is not important. And therefore, we go to the second order correction. Now, without that little thing there, I do have minus a sum over all m different from 0. So technically means overall n1, L1, m1 different from the 1, 0, 0. And overall n2, L2, m2 different from the 1, 0, 0. Okay? This is what it means. Okay. Then I have what? I have, well, this element here I can just put outside. So it's now plus 1 over the ground state of the unperturbed thing, which we discussed is minus 2 Rydberg. Okay? I can put that out. Then I have what? I have this object. I have the 1, 0, 0. 1, 0, 0. So the state to the right. Then I have V. Then I have N1. Sorry, it's long to write, okay? But not difficult. Okay? And then I have the same thing star, so psi N1, L1, M1, psi N2, L2, M2. Then I have V, and then I have again 1, 0, 0, 1, 0, 0. Okay? This is the numerator, okay? Modulo square, which I have rewritten as itself times the star. Now, the sum is still restricted. You should avoid 1, 0, 0. But what about if I put also 1, 0, 0? Do I include anything bad? Really not, because the matrix element is 0 for 1. If these are 1, 0, 0, 1, 0, 0, I know from first-order perturbation theory we discussed a second ago, this element would be 0. Okay? So I can even remove this restriction. Okay? This does not change at all my calculation. And now this is beautiful. Why is beautiful? Because the sum, okay, now acts on this object here. The sum over all possible N1, L1, M1, N2, L2, M2 of this state. What is it? The usual identity. Okay? Okay. Good. So this is an identity. So you see the trick. By removing something that was depending explicitly on these numbers NLM, and therefore making the whole thing just a sum with only states appearing, okay? And adding something that is indeed 0, the matrix element when this is 1, 0, 0, I was able to extract an identity out and therefore conclude that this object is equal to minus 1 over twice the Rydberg times what? Now, a simple enough matrix element. It is 1, 0, 0, 1, 0, 0, V times V, okay? So V square. So this element square. So first of all, I have x1, x2 plus y1, y2 minus twice z1, z2 squared. That's not enough. I have also e square over r cube squared. So let me put it here. E square over r cube squared. And then I have 1, 0, 0, 1, 0, 0. Okay? Yeah. Which term? Oh, because I didn't know how to do the calculation. No, this is, this is one reason. There is a deeper reason, is that this one is much smaller than that. Smaller, say, okay? At least a quarter of that small, and if you go up and up, it's smaller and smaller, okay? So I decided that since they were smaller, and I didn't know how to do it with them inside, I just dropped them, okay? Huh? This is minus a Rydberg. This is minus a Rydberg over 4. So at least if I put the electrons excited, at least I lose 3/4 of the energy. Okay? So this thing is at most 1/4 of that. But 1/4 is a small number. Just forget it. It's not exact. But even the full thing is not exact. You realize the behavior, okay, is still with the square of this matrix element. So the behavior of 1 over r to the power 6, this is untouched. This is true in second order, no matter what I do. It's only the exact coefficient, okay? So I am arguing with you that this object in front is minus 1 over 2 Rydberg e square over e square to the power 2 over r to the 6. Now, the coefficient that multiplies 1 over r to the 6 should be obtained by a careful sum of all elements like this, with the denominator there included. I don't know how to calculate that, however, and I prefer to get a number, whatever number it is. Okay? A crude number is better than no number at all. That's a rule in physics. Okay? So whenever you don't know what to do, you are legitimate to just throw away something and see what happens, especially if you argue that that something maybe is small. Okay?
We should add the constant
I add nothing. I just eliminated this. Okay? With this eliminated, now everything is equal signs. Okay? It's an approximation of this, obviously. But once I do that approximation, everything here is equal. I don't know if you should add nothing here. There is no plus.
No. Okay. Multiply by some constant.
Well, you have lots of constants. You have E squared, the 2, the Rydberg, this matrix element. So there are still lots of things.
But the one coming from E minus EM 0. You said we neglect this term.
That is not a constant. It's a constant inside the sum, and the constant depends on the index. So it contributes. The final destiny of that number is minus c divided by r to the 6. The way I calculate the c, okay, in principle requires a detailed calculation of each single denominator there, okay, the ones you love. There. I should calculate them all and sum appropriately. Now, this will give me some exact, so to speak, second order expression. Now I am approximating this with something like minus c over r to the 6. So same behavior, but the c is different. And the c is this. Okay? Is this clear? Is this clear? So the C that I am providing to you is given by this integrals. Okay? It's not the exact C because I have done a crucial approximation there. I have thrown away something. And therefore, the exact C would be different. But certainly the order of magnitude is correct. Okay? So we'll see in a second the physics, in fact, of this matrix element. Okay. So how do we calculate this? Well, still looks a little bit clumsy. First of all, there are, from squaring this, there are many terms. Okay? Nevertheless, you should notice that now, for instance, when I square a term like that, I would obtain also objects like x1, x2, y1, y2. Okay? Now, you know, x1 and y1 take care only of, say, 1, 0, 0, 1, 0, 0 for electron 1. And the other two also have to be sandwiched between 1, 0, 0 and 1, 0, 0 for electron 2. Now you immediately notice that now you have a revenge of the odd thing, because this is odd under x and this is odd under y, while this is even under everything. Okay? So by dividing the space into two semi-plane, you can immediately argue that, for instance, this is 0. Okay? So this quantity, all the mixed terms are 0. Okay? So the only term that survives is, for instance, the square of this plus the square of that plus 4 times the square of that. The 4 is due to the minus 2 squared. Okay? So the mixed term where x and y or x and z appears are 0. Only x squared or y square or z square are even to the point of, satisfaction that you can claim they are different from 0. All right? Good. So first of all, this is the first simplification. Second simplification, these are spherically symmetric functions, okay? So you understand that the matrix element of x square, for instance, should be the same as the matrix element of y square or the matrix element of z square. Makes no difference, right? So in some sense, the crucial matrix element that I really need is this. Once I have this, I'm done, okay? Because everything else is related to this, okay? So the matrix element that I need is this, accompanied by, obviously, a friend for electron number 2, but the electron number 2 will have exactly the same contribution. So it's this square, okay? This term will give me this element squared. Now what about this? This will give me exactly the same contribution. And this will give me exactly the same contribution with a factor 4. So all in all, 1 plus 1 plus 4, 6 of those objects appear. Okay? So hopefully I have not confused you too much at this point, and you realize that what I have here is minus 1 over twice the Rydberg. Then I have e to the 4th, r to the 6th, and then I have 6 times the matrix element of x square or z square, whatever, that doesn't matter, between 1, 0, 0 squared, okay? And that's it. This is it. Yeah. This one? Well, let's consider this integral. X 1, y 1 between 1, 0, 0 and 1, 0, 0. This is a totally spherically symmetric function. So let us see. In the plane, for instance, x and y, okay? This function is positive in this region, okay? Because both x and y are positive. Now, if you change x into minus x while keeping y positive, this becomes negative. Okay? Then you change y also, and this becomes again positive. But if you keep x positive and y negative, it is negative. Okay? So for every point, there is a corresponding point where the function is negative, another one where it is positive, and another one where it is negative. Okay? But the value of the function, which is spherically symmetric, is the same everywhere. Okay? So for every plus, there is a minus, and for every minus, there is a plus. Okay? And so it's more complicated than an odd function, but still a kind of odd function. Okay? A function with equal amount of positive and negative contributions. Okay. Or you could be even more sophisticated. For instance, this operator is, you can define, for instance, the reflection under, say, the y-axis. These are not parities, but they look like parities, okay? So you just change one coordinate. They are unitary operator. How these things behave under reflection, they are just even. How this thing behaves under reflection, odd, okay? So you can make the argument even more transparent and clean by just using a little bit of the machinery of unitary operators, symmetries, and things like this. So this function here is evidently odd under some of the obvious reflection under, say, change of x into minus x or y into minus y. And while the function there is completely even. All right? Is this clear? Yep.
In this case, okay, I don't understand how x1, x2, are they the same? Because when you take the square and treat them,
They are variables in an integral. Remember, I have an integral which factorizes into 2. Now, do you mind if I call this variable R1, or I call it John, or I call it R15? Okay? It doesn't matter, right? It's an integral. You integrate. Now, strictly speaking, what matters is the labels that you have there. But the labels is the same. It's 1, 0, 0, 1, 0, 0. So it's the same integral, really, okay? Written with two different labels. One I call it x1, the other I call it x2. But integrated over all the space points, and therefore you can change label, and that is exactly the same integral, all right? So you shouldn't be confused by the label in this case. They are the same integral, okay? In fact, here I even omitted the label. I mean, it's just x, okay? Call it x. Or z. By the way, x, y, and z, now, do you understand why they are the same? Okay? The integral of x squared and the integral of y squared and the integral of z squared, they must be the same. Okay? Well, finally, you can calculate this number, okay? And you will see that, well, let's try to estimate. This is the integral of z squared in between two 1s wave functions. The 1s is an exponentially decaying thing on a scale of the ball radius, okay? Now, it will be something times this integral is a length squared. So this will be the ball radius squared times some factor. And the factor is 1. Okay? So this is exactly a ball radius. You might say, okay, but how do I calculate the z squared? For instance, z is r times the cosine. I should do the calculation of the cosine. Well, you can do it. Or notice that this is 1/3 of the sum of the three, x, y, and z squared, which is 1/3 of the r squared. So you don't even, you need just to calculate the integral of r squared and divide by 3. Whatever you want to do, the result is very simple. It's just the ball radius square. So all in all, what you have is the following. This quantity is equal to minus 6 e square, the ball radius to the power, sorry, e to the 4th. The ball radius to the power 4, r to the power 6, and twice the Rydberg. Twice the Rydberg is the Hartree. And you know that the Hartree is e squared over the ball radius. Okay? So really, e squared and e to the 4th cancel, and you have minus 6 e squared ball radius to the power 5th over r to the power 6. Okay? Now, does this make sense? At least dimension are right? Yes, they are. It's e squared over a length. But this length, r to the 6th, multiplied by ball radius to the 5th. It's a reasonable thing, right? In fact, in retrospective, if I had to estimate this thing, what could it be? I mean, the only lengths that you have are r, the ball radius, and then you have to construct energies e squared. So what else could you use if you know that you should have r to the power 6 downstairs, a ball radius to the power 5, times some constant, which happens to be 6, but this is only approximate, okay? The exact one would not be 6, would be whatever, 6.32 or any other number. Do we care about this constant? No, we don't, in some sense. We want to understand the physics of this thing, which is pretty transparent from this clear. The exact calculation then would really require many sophistications. You should worry about other things, and in the end, it's not particularly neither important in this context nor illuminating. Okay? Questions? Okay? This is a rather complicated exercise. Well, not complicated. I mean, the thing is, but there are several steps. In particular, there is a complication of having two electrons. Nevertheless, the full result, so the van der Waals attraction of two neutral atoms shows the quantum mechanical nature of this attraction, for instance, okay? And due to the essentially dipole type of, you see, these are dipole matrix elements, because this is 1s and this is p. And this in the middle is a dipole operator. The dipole is E times the position, okay? If you have two charges, the difference. Okay, so the atom has a dipole because there is a plus and a minus. The element of the dipole appears in the important matrix element that have to be squared, so dipole-dipole, and the result is 1 over r to the 6, because the dipole itself goes like 1 over r to the 3rd. All right. Yeah. No, it's not a spin interaction. The two atoms are, in fact, in this case, I mean, pretty featureless, but no, it's not a spin interaction. Okay. Yeah. No, the answer is no. Yeah. Other questions? You would like to know why this interaction does not depend on the spin? It's a good question. I mean, in fact, you might think, well, maybe if the two spins, okay, put themselves in certain configuration, then this is better. However, well, first of all, they do put themselves in a certain configuration, which is up-down. So they don't do up-up, for instance, okay? Nevertheless, there's not much freedom. I mean, in principle, you might say, okay, they maybe arrange their configuration in such a way as to gain energy. But these are very small energies that you could think of gaining. And they have to compete against very, very large splittings. So, okay, so the splittings are Rydberg type of things, okay? So if you mess up with the orbital, you pay a lot. So you certainly don't want to go and look for exact spin details by messing up with the orbitals. And so the actual calculation to all orders, I don't know exactly how it looks like, but I would imagine that, I mean, to lowest order, certainly there is no spin dependence. I mean, except for this obvious dependence, the fact that the overall spin is a singlet, okay? So the combination of the two atoms is in a singlet state. A triplet would be a different state, okay? A triplet, for instance, would be in a state that has to have a wave function that is anti-symmetric, and therefore must be some excited state, for sure. Okay? So what you can say is that there is a spin dependence in the sense that the singlet is the ground state. The triplet would be somewhere excited. So this, in some sense, justifies the fact that the interaction depends a little bit on the spin, in the sense that the ground state really is singlet. The other states are triplet. So the spin here is kind of a spectator, but not an innocuous spectator, because it dictates a lot of things, okay? For instance, it dictates the fact that the wave function of the ground state is this, and is symmetric under thing. So it looks like it's disappearing, but it's really not disappearing. It's playing part in the game. By Pauli principle and all these things are really strongly spin entangle. So I don't know if this was a satisfactory answer. In some sense, it's still too early in our knowledge of many particles to discuss this in more detail. What I want to point out is that the spin is like if it disappearing, but leaving a strong trace of its presence through Pauli principle. And therefore, for instance, the fact that the ground state is a singlet and not a triplet is a spin-dependent type of effect in some sense. Okay? Yeah. No, the point is this. If you take it to be up, okay, up, then what is here could not be 1, 0, 0, 1, 0, 0. Okay? Should be, for instance, 1, 0, 0, 2, 0 something, plus or minus the exchange of the two. So you see immediately that you pay some energy, just a quarter of a Rydberg at least, in order to have a triplet. Okay? So that's a substantial energy. Okay? We are discussing here about small correction to the -2 the Rydberg. And there you immediately, by changing the spin, you pay a quarter of a Rydberg at least, which is a lot. This is a small quantity. Remember, R is much bigger than AB. Okay? So you see, R is much bigger than the Bohr radius. So this quantity is much smaller than the Rydberg. The correction to the Rydberg is much smaller than the Rydberg. Otherwise, this would not be a sensible, perturbation calculation. Okay? I don't know if this was clear from my discussion. What I say is that this must be much less than in absolute value than the Rydberg. Okay? So only for R sufficiently large, this is a reasonable thing. Okay? Today, life is complicated by this music in our ears. Okay? So I don't know if I answered the thing. So the spin enters in some sense. Okay? So it's not that it's not there. But it doesn't show itself in a very explicit spin-spin dependence. Okay? Yeah. Does it depend on? The question is if this van der Waals interaction is strongly tied to the fact that these are hydrogen atoms. The answer is no. Any neutral type of atom, molecule, neutral and not having a permanent dipole, okay? Because what you have here is that the isolated atom is neutral and without a permanent dipole, obviously. The charge is completely... And so you expect that at least this thing should, interact very, very with higher multiples, okay? If you have a permanent dipole, then you expect already that this dipole with the other dipole will see each other and they will interact and that's it, okay? But here there is really no dipole, okay? So you might expect, okay, maybe there is no quadrupole, no, maybe just no interaction. Well, no. The dipole is kind of induced and fluctuates quantum mechanically in some sense, okay? But it's not important that this hydrogen. The same calculation would apply to, I don't know, to two other neutral atoms, spherically symmetric, if you take two neon atoms just to suggest a completely filled shell atom, to helium, to xenon, or whatever, okay? That would be exactly the same, but I think it's even more general. In fact, two pieces of uncharged solids they attract each other. In some sense, there is an effect that is called the Casimir effect. This is also related to this thing, okay? So uncharged objects, they kind of feel each other at long distances. Okay, so more general than what I did.
If you take two atoms, where you have many electrons, in our expression of dipole, okay, in our expression of the potential, how we wrote it, the interaction electron filters. So in this case, in the case we have many electrons, how should we?
Well, if you go back to your electromagnetism, probably you have done something like this. It's called multiple expansion. There is, I'm sure, one page or one chapter of your favorite electromagnetic book in which they pose the following question. Suppose that I have a certain charge distribution here and another charge distribution there. And these two charge distributions feel each other with the Coulomb potential. What is the potential they feel? Okay? So it's, technically speaking, the integral over, say, R1, the charge distribution in R1, the charge distribution in R2, divided by R1 minus R2. Okay? So here is the first piece, and here's the second piece. How do I keep track of the possible contributions? And you learn that there is a systematic way of, say, expanding essentially this thing for large separations and seeing what is the total charge here, for instance. So the total integral is important. This will determine if this interaction goes like 1 over the distance. Total charge times total charge divided by the distance. Okay? Then the next term in the multiple expansion is, for instance, charge and dipole and dipole-dipole and dipole-quadrupole and quadrupole, all kind of possible higher moments of the charge distribution, okay, enter in general in the expansion. And this is all a game of spherical harmonics, because you probably remember that you can expand this thing, okay, into for very large R1, a very large separation of the two things into sum of products of spherical harmonics times, I forgot exactly, probably Bessel functions entering, whatever, okay? So electromagnetism answers your question. I see what you are worried about. I mean, this looks like a continuous charge distribution, which is reasonable in electromagnetism. Here you have electrons, so point charges. Well, you can see this as a sum of delta contributions at the position of the two electrons and derive what is the expression. You are worried about how do I do this calculation if I have 32 electrons on one atom and 32 on the other. What do? I calculate 32 squared possible terms. And well, obviously there are techniques related to multiple expansion that allow you to calculate the dipole, okay, in terms of the position of the thing, and you just have to multiply the two dipole and divide by r to the cube, all right? So the expression in the end is the dipole operator 1 times the dipole operator of the other divided by r cubed. Well, obviously, I mean, the dipole operator, well, let me call it D1, of the electron 1, dipole operator 2 minus 3 times R dipole operator 1, R dipole operator 2 divided by R cubed. Okay? So if you work enough, I'm pretty sure that this in the end will come to be, where these objects are operators for a single atom. Okay? Dipole operators for the single atom. It's a more complicated thing. You don't think that life is simple. I mean, many electrons, you wouldn't be able to calculate, most probably, anything of this. But at least in principle, hope it's clear that it's similar in spirit to what we have done. Okay? How is? I do not understand the question.
Okay, we have two distributions.
Mm-hmm.
From this formula, we see that R cannot be 0. At R, yes?
This one?
R, yes. R cannot be 0.
Not only cannot be 0, these are meant to be expansion for large R. If the two things are close by, forget it. Just calculate everything. Okay? I have two atoms close by. I should have all terms in the Hamiltonian. Nothing saves me. Okay? I can do simple perturbative approaches like this when the two things are separated. All right? Is this clear? Otherwise, I have a molecule. Okay? I go to a friend, a quantum chemist, and I tell him, please calculate for me this molecule. Okay? It's complicated stuff, not simple. Complicated calculations. Next year, next course. Every single thing you can think of is a complicated problem, boys, okay? Complicated stuff. Complicated stuff. Once you have more than one electron, life is a mess, okay? Even the single helium atom is already quite complicated, okay? Not impossible, but quite complicated. If you have 3, 4 electrons, you go to a friend who has a computer, and you please ask him to calculate things for you. You wouldn't be able to calculate anything, almost, by just pen and paper, okay? So, but there are approximate Hartree-Fock things, but really sophisticated machineries that have to be dealt with care, and not always giving you sensible results, okay? So don't ask again, what if? What if is complicated stuff, okay? I select for you here simple problems. The square well, the harmonic oscillator. What if I have a black hole in the... It's complicated, okay? Complicated. Okay, so we have essentially exhausted with, you are masters, obviously, in asking. No, I'm kidding. I mean, the questions are interesting, obviously, but in some sense, the answer is always the same, so it's less interesting. So what I will try to do next time, if you allow me, by refraining from asking too many impossible questions, is the degenerate case, okay? So until now, we saw how to calculate essentially second-order corrections when the spectrum of your initial system is non-degenerate. So each level, one state. There are many cases, including, obviously, hydrogen, where the spectrum is highly degenerate. One level, several states. So what do I do? The energy denominators would be zeros, okay? Because the labels for the states are different, but the energies happen to be the same. So I cannot use the formula I just did before. But luckily enough, there is a way of doing perturbation theory in that case also. It requires diagonalization of a small subspace of degenerate levels. And this is something that, I mean, in practical cases often can be done reasonably easily. Okay, so we'll do this next time by studying the linear Stark effect. So what happens to an hydrogen atom if you put an electric field, okay? Not the harmonic oscillator with the electric field, now the hydrogen atom, so something real, okay, with the electric field. And then we will study, finally, the fine structure of hydrogen, okay? We discussed already the form of the perturbation. Now we'll do the calculation, which is how to use that perturbation and actually producing numbers. Okay? And this hopefully tomorrow. Okay.